Good afternoon, everyone. I hope you had a good weekend. Today we're going to start out by talking about the Doppler effect. Now, some people say the Doppler effect is kind of spooky, so I have a whole slate of spooky examples planned for us today. So the idea behind the Doppler effect is that if you are standing, let's say you're standing at one end of a football field and your friend is standing at the other end, if an object is moving, say, from you to your friend, if it's going fast enough, the two of you could hear different frequencies if it's making a sound, or if it's going extra fast, you could see potentially different colors if it's emitting lights. So we're going to look at today kind of why that is and how that works out mathematically. So we're going to start with a conceptual sketch to kind of work out why the Doppler effect happens. And to help us with this, we have our friends Mulder and Scully. So Mulder and Scully are standing across from one another in a park, and someone sends a frisbee flying by, and the frisbee goes past Scully and now it's heading toward Mulder. Now this frisbee happens to have a little red light attached to it, and it blinks on and off. So every so often it blinks and you have some red light and then it blinks off. So just blinking on and off. Now our frisbee is going to start out here at this point x1, that's when we're first pay attention to it. And so at that point the light blinks on, so some photons are emitted. And we know that light travels in waves, so the light particles, the photons, are going to travel outward in spherical waves. So by the time our frisbee gets to point 2, our original little dot of light is going to have spread out now. And we don't know how fast our frisbee's going, but we know that it's going slower than the speed of light. So the front of our light wave has to be farther out than our new frisbee location. So we could represent this by drawing a little circle to represent the spherical waves that are coming out from that point. Now, when our frisbee gets to the point x2, it's going to let out another, it's going to blink on again. So we let out another pulse of photons, or another bunch of photons, and so these two are going to spread out, and this wave here is going to continue to spread out over time. So as time goes on, this one gets more spread out, but we're also going to have a wave that comes from this location. So if we hop ahead to when our frisbee reaches the point x3, it's going to look something like this. So our new point, x2, its wave is going to look something like this. It's going to have spread out, and so it's going to do something like this. And our original one, this one's still centered around x1. So this one's centered around x2 because there's a batch of light that's emitted there. This one's still centered around x1, so and it's going to be wider now, so it's going to look something like this. So you can see we're going to get some circular shapes, but they're a little bit lopsided. They don't fit nicely centered because this one is keeping going. So we can now look at what happens. So our frisbee reaches the point x3, it blinks on, and then it goes ahead to somewhere else. And what happens there? Well, we're going to see the same kind of trend. So our two waves that were emitted at x1 and x2, those are going to keep spreading out. And now we're also going to have a new wave that was emitted at x3. And so it's going to look something like this. And these circles should be symmetric. I'm trying to draw them as best as I can, but and so then we have another circle that's centered around the point x2. And then lastly we have one that's centered around the point x1, and it's going to do something like this. So you can see that on this side our wavefronts are kind of bunched up, and on this end they're kind of spread out, and they should be symmetric. My drawing skills are just not that great. So our original wavelength is going to look something like that. And again, the circle should be symmetric. It got a little lopsided because I was trying not to hit the x3 and x2, but this should be a circle, and so centered about that blue dot in the middle. Now over here, this is a wavefront and this is a wavefront, so we have a wavelength here. And we're going to call this one lambda sub plus. And so when we have an approaching wavefront, we use a plus subscript. And over here, these ones are kind of spread out, so we're going to have lambda with a subscript minus to denote that they're moving away from us. So are there any questions on this idea so far? So when we have an object that is coming toward you, the wave fronts are going to kind of get smushed together, so we have a shorter wavelength, and when it's moving away from you, they're going to spread out, so we have a longer wavelength. Now, we learned last week in lab that frequency and wavelength are inversely proportional. So if over here our wavelengths are getting smaller, our frequency is going to get bigger. And over here our wavelengths are going to get bigger. That means our frequency is going to get smaller. And so when we look at equations for our frequency, we're going to see, and we're not going to do the full derivation, but we will see that the one for these ones is going to give us a bigger frequency, and the one for going away is going to give us a smaller frequency. So now the book has 4 different equations for the Doppler effect. They have 2 equations for a stationary observer and a moving object. So you're standing still and an object is moving either toward you or away from you. So they have one equation for toward, one for away. They also have stationary object moving observer. So, you know, the frisbee is sitting on the ground and you're coming toward it or moving away from it. We're going to be focusing on stationary observer moving object. So we're going to kind of be skipping the other equations. So those ones we generally don't really use in this class. So we're going to focus on you're stationary, there's an object that's either coming toward you or moving away from you. But the book has the others as well if you end up needing those for some reason. So the equations look like this. So when we have an object coming toward us, our frequency is given by the frequency of when it's stationary divided by 1 minus the speed of our source divided by our wave speed. So we're going to write out what each of these things are. So F plus is going to be our observed frequency. F sub s is going to be the frequency that we would measure if it was stationary and we were stationary. So it's our stationary frequency. And then V sub source, that's the speed of our object or our source. Now the book uses a little subscript s for this, but we've previously used V sub s for the speed of sound, so to kind of prevent confusion I've written out source here, but they use just a V sub s and it means the same thing as V source here. Now the last thing is our wave speed. And that's why I think it helps to clarify that this one is source, because if we have sound waves traveling, the wave speed is going to be what goes into this speed down here, not up here. So that's the expression for when we have an object that's coming toward us. Now, if it's moving away from us, we have a very similar equation. The only difference is we're going to get a plus sign instead of a minus sign. So for an object moving away, we have our frequency is equal to the frequency when it's stationary times 1 minus, or plus now, speed of our source, divided by our wave speed. So are there any questions so far? Alright, so let's do a couple examples. And for our first example, we're just going to go back to Mulder and Scully and the Frisbee. And we'll put some numbers to it. So let's suppose Mulder and Scully are standing in a park across from each other, and someone throws a frisbee, and it goes zipping by past Scully toward Mulder, and it's traveling at a speed of about 34 meters per second. Now this is the speed of our object, which is our source, so we're going to give this a little subscript source here. The frequency of red light is 4.3 times 10 to the 14 hertz. And so we want to know what color will the light appear to be in Scully's frame of reference. So the first thing, the frisbee is moving away from Scully, so we're going to want to use the equation for when it's moving away. So that's our F minus equation, and that's equal to F sub S divided by 1 minus V source over V. Now, it may seem like we don't have enough information, but since this is light that's moving, the wave speed is going to be the speed of light. So we actually do have enough information, we're just not told explicitly. So one thing to be aware of is a lot of times you'll have sound in air or you'll have light, and you won't necessarily be given the speed. So if you're not given the speed, you'll also have to remember that light moves at 3 times 10 to the 8 meters per second, and sound in air is about 343 meters per second. So we're going to go ahead and plug our values in. We'll have 4.3 times 10 to the 14 hertz divided by 1 minus 34 meters per second over 3 times 10 to the 8th meters per second. And we plug this into our calculator, we're going to get that our frequency is equal to 4.3 times 10 to the 14 hertz, which is the exact same number we had before to any important number of sig figs. So what happened? Well, light moves really, really fast. So this number here is something very, very small, very close to 0. And so if we're subtracting off what's basically 0, then we have 4.3 over times 10 to the 14 hertz over 1. That's basically still 4.3 times 10 to the 14 hertz. So to get a color change, you would need something that was going at a significant fraction of the speed of light, which most things are not going to be able to do. So are there any questions on this first example? All right, so we'll move on to another example. So for our next example, a clan of vampires has moved into your town. The vampires transform into bats at night and fly to seek out their prey. Visually, the vampires' bat forms are indistinguishable from the common bats that live in your area. When stationary relative to a stationary observer, both have calls of frequency 60 kilohertz. So our stationary frequency is 60.0 kilohertz. Local scientists have reported that local bats travel at an average speed of 100 kilometers per hour. So the bat's speed is 100 kilometers per hour. You have read that vampires in bat form travel at a speed of 120 kilometers per hour. So the vampire is 120 kilometers per hour. If a bat is approaching you, would you be able to determine whether it is a common bat or a vampire using only your frequency meter? So to do this, we're going to have to figure out what the approaching frequency would be for both a bat and for a vampire in bat form. But before we get to that, we're going to need to do some conversions because none of these are in our standard base units. So this one's kind of more straightforward. Kilohertz means 10 to the third. So we just need to multiply this by 10 to the third, and we're going to get that frequency is equal to, and then we're going to have 6.00 times 10 to the fourth hertz. Now, these two are going to be a little bit more involved to convert because we have to convert kilometers to meters and hours to seconds. So we'll do an example with the bat, and the vampire works the exact same way. So we have 100 kilometers per hour. Now we have 1,000 meters in a kilometer. So that's going to take care of the kilometer bit. And then we have in 1 hour, that's 3,600 seconds. So if we plug this into our calculator, our bat speed is going to be about 27.78 meters per second. We're going to do the same conversion process for our vampire. And so we're going to have that our vampire speed is now 33.33 meters per second using that same conversion process. So are there any questions up to this point? All right. So the bat is coming toward us, so we need to use the approaching equation. So and we'll do side-by-side comparisons of the two different calculations because we need to do one for the bat and one for the vampire in bat form. So we know that our frequency when we're approaching is our stationary frequency times 1 minus speed of the source, which in our case is either going to be the bat or the vampire, divided by the wave speed. Now our wave speed here, since this is, we're talking about the frequency of sound, that's going to be the speed of sound in air for both cases. So we'll start with our bat, our common bat. So F plus is equal to, we said that their call when they're stationary is 60.0 kilohertz, so which is a 6.00 times 10 to the fourth hertz. And then we have 1 minus, our bat is traveling at 27.78 meters per second, which is what goes in our numerator. And we're going to divide by the speed of sound in air, which is our 343 meters per second. So again, the problem didn't explicitly state our wave speed. We had to recall that this is sound in air, and so look in the textbook and see the speed of sound in air is about 343 meters per second. So we plug this into our calculator, and then we get that for our bat, it has a frequency of about 6.53 times 10 to the fourth hertz. Now for our vampire, this is going to be the exact same process. The only difference is going to be the number that goes in here. So we have F plus is equal to 6.00 times 10 to the fourth hertz divided by 1 minus, and then we have 33.33 meters per second divided by 343 meters per second. And so for our vampire, the frequency we hear would be about 6.65 times 10 to the fourth hertz. So if we're dealing with vampire here instead, we have we're going to hear a higher frequency. And so could our frequency meter tell the difference? As long as it can measure to 2 sig figs, we're good. If we can't, then if we only have 1 sig fig, then we're getting eaten. But as long as we get 2 sig figs, we're good. So are there any questions on this problem? Alright, so I have one more Doppler effect question for you, and then we'll be moving on to some other material. Alright, so let's suppose you're walking along an old logging trail late at night, and you hear a werewolf howling at the full moon. Your frequency meter detects a frequency of 380 hertz. There is only one werewolf in your town, and when you last encountered it, its howl registered on your frequency meter at 350 hertz while the werewolf was stationary. Based on your current frequency reading of 380 hertz, is the werewolf moving toward or away from you, and how can you tell? So that's our first question. So our current frequency is bigger than our frequency when it's stationary. Well, if we think back to what's happening with our wavelength, we know we can see this in a couple different ways. So we know that V equals lambda F. So to make F bigger, lambda would have to get smaller. So if that's the case, then it has to be moving toward you, because remember, when it's moving toward you, that's when we get the short little compressed waves. So it's approaching, and we can see that because we can see that lambda would have to get smaller to maintain the speed of sound the same number if frequency gets bigger. So that's one way of looking at it. The other way we can look at this is if we look at the equation for when we have something that's approaching. We know F plus is F of our stationary situation, 1 minus V source over V. Now if we look at our denominator here, our speeds are going to be positive numbers. So if we're subtracting a positive quantity from 1, and our speed of our werewolf is probably not going to be bigger than the speed of sound. So this is going to be some number less than 1. So we have 1 minus some number that's less than 1, but still between 0 and 1, still positive. Our denominator is going to get smaller, which means our frequency as a whole will get bigger. So that's another way of looking at it that leads to the same answer. Our werewolf is approaching because this denominator will get smaller, making this frequency bigger. So our werewolf is approaching. Alright, so now we know our werewolf is approaching. We can give this a little subscript plus. And so we might want to also know how fast is our werewolf traveling, and is that speed realistic? So to figure out how fast our werewolf is traveling, we're going to have to take our equation, our F plus equation, and rearrange it. So we know that F plus is equal to Fs divided by 1 minus V source over V. We want to solve out for our werewolf speed, which is V source. So the first thing we're going to do is we're going to go ahead and multiply both sides by what's in the denominator. So we're going to have F plus times 1 minus V source over V is equal to, and that's going to leave us with just F sub s on this side. Now I'm going to go ahead and divide both sides by F plus to get rid of that from the side. So we're going to have 1 minus V source over V is equal to F sub s over F plus. Now the next step, I'm going to do two things simultaneously. I'm going to add V source over V to both sides so I can get it off of this side. And I'm going to subtract Fs over F plus over to the other side. So we're going to get that 1 minus Fs over F plus is equal to V source over V. So I just move this term and also move this term both at the same time. So we're almost there. The last thing we have to do is multiply by our wave speed so that we have V source by itself. We're going to get that V source is equal to V times 1 minus F sub s over F plus. So that's the equation we're going to be working with. So I'm going to rewrite the equation on this side of the board so we have a little more room to work with to plug our numbers in. And so we're going to have that our werewolf speed is equal to, well, the speed of our wave. We're talking about the werewolf's howl. That's a sound, so it's going to be the speed of sound in air. So 343 meters per second. So again, we were not explicitly told the wave speed. We had to use the fact that it's sound and remember the speed of sound in air. And then we're going to have 1 minus, now when our werewolf is stationary, its call is, or howl is 350 hertz. And then the howl we measure now is 380 hertz. We go ahead and plug this into our calculator and get that the speed of our werewolf is about 27.1 meters per second. Now it's a little bit ambiguous how many sig figs we have here because these are both rounded numbers, so we could say that we have only 2, or we could try and argue that there are 3. So we could also say this is 27 meters per second. Either of these answers would be acceptable. So the last part of the question was, is the speed realistic? Well, werewolves aren't real, so we could say yes, werewolves can go really fast, it makes sense. But if you look at the speed that wolves travel at, kind of the upper limit on a wolf's speed is about 16 meters per second, at least from my brief Googling online yesterday. So perhaps it's not that realistic. And another possible explanation could be this is about the same speed that a car travels at. So maybe our friend was driving down the logging rodents started transforming into a werewolf while they're driving, and so that's why their howl is traveling at that speed. Are there any questions on this one? All right. So if there are no questions on this, we're going to hop back to a topic we covered briefly last week. We're going to need it for a lab this week, so we're going to just kind of refresh our brains. So this week's lab is going to be on wave speed versus tension. And we learned last week that if we have a wave on a string, the wave speed is related to the tension and the linear mass density. So it was equal to the tension divided by the linear mass density. Now, if we're thinking about what we're going to want to plot when we do this in lab, we're going to want to rearrange this a little bit because this isn't convenient to plot. So I'm just going to start by squaring both sides. So we're going to have v squared is equal to tension divided by linear mass density. And then I'm going to multiply both sides by mu, and so we're going to have that t is equal to mu times our speed squared. So if you go straight to just plugging tension, or plotting tension versus wave speed, you're going to get kind of an ugly curve. And if you're wondering how you can make this how you can linearize this, if you plot tension versus wave speed squared, that should give you a nice linearized version where your slope is going to be the linear mass density. And I believe next week we're going to be doing wave speed versus linear mass density, so it's going to be something very similar to what you do this week. We'll just want to rearrange the equation slightly differently. So are there any questions on that? All right, so now we're going to move into our last topic for the day, which is standing waves and superposition. So we're going to focus on linear superposition, and the idea of superposition is basically just when you have two waves that meet, you add the overlapping pieces together mathematically. So let's suppose we have a couple of waves . And so I'm going to draw one of our waves in blue and the other in red. So our first wave is just going to be a rectangular wave. So it's going to go kind of along the y-axis up to a height of 1 meter. It lasts for 2 meters, and then it kind of drops back down. So that's our first wave. Now our second wave is going to be kind of funnily shaped. It's going to look like this. So it's going to start over here at 3 meters. It's going to have an amplitude of 2 meters. And then it comes down like this, drops down to 1 meter, and then it goes at 5, and then it goes back up to 2 meters, and then it drops back down. So those are our two waves. And let's suppose the blue wave is moving to the right at 1 meters per second. So this one is going at 1 meter per second to the right. And our red wave is moving at 1 meter per second to the left. And so after a second, we want to know what is our wave going to look like. Well, our first step is we're just going to go ahead and draw how the two waves are going to shift over. We're not going to worry about adding them yet. So we're just going to redraw our graph here. Now our blue wave is moving to the left, or sorry, to the right. So it's basically just going to be, it looks the exact same, but it's going to be moved over here. So for the blue one, it's going to look like this. And then our red one is going to do the same thing. So all the points on the red wave are going to shift 1 meter to the left. So it's going to look like this. And so we can see from between 1 and 2 meters, it's just going to be look like the blue wave. And between 3 and 5 meters, it's going to look like the red wave. But what's happening at this region in between? How do we represent that in between region? Well, the way we can do that is by adding them, adding their y coordinates, basically. So I'm going to draw another graph, and we're going to go ahead and we're going to start by drawing what we know. And then we'll worry about that middle region that we don't know. And so for between 1 and 2, we're just going to have something that looks like this. And then at 3, it's going to look like this. And so now we have to worry about the middle region of overlap. And I'm going to go ahead and grab a purple marker for this. Let's get some new whiteboard markers over the weekend, a whole rainbow of them, so pretty excited to be using them. And we're going to use purple here because red and blue make purple. So if we think about what's happening here, so at the point x equals 2, our blue wave has a constant height of 1 meter in the y direction, and our red wave is up at 2 meters. So if we add those together, 1 and 2 would give us 3. So our resulting wave is going to be up here at 3. So we're just going to draw that point on here for starters. So that's where our wave's at. Now if you look at the end of this, well, the blue wave is still a constant 1, so we're just adding a constant 1. This one's at about 1.5, it looks like. So 1 and 1.5 would give us 2.5, so at 3 we should be at 2.5. Now basically, since this one here, this top of this rectangular wave is always adding a constant 1 to this, we're just going to mimic that same slope, because every point along there is going to get 1 added to it. And then we're just going to connect back to our curve like this and like this. So that's what our graph would look like after 1 second. So are there any questions on that? All right, well, if there are no further questions, that's all the material I have planned for you for the day. So enjoy the rest of the day and don't hesitate to reach out if you end up having other questions at some point in time. And I'll see you on Wednesday.